Have you ever wondered what will power our future?
Especially with the huge demand for energy storage. While lithium-ion batteries are everywhere, scientists are looking at a promising alternative: sodium-ion batteries.
That's right. Sodium is one of the most abundant elements on Earth, making it much cheaper and more sustainable than lithium. This cost advantage is a huge deal for large-scale applications like storing energy for the power grid.
And they work on a similar rocking chair principle as lithium-ion batteries, where sodium ions shuttle back and forth between the cathode and anode during charging and discharging. The key difference is that sodium ions are larger and heavier than lithium ions, which presents some unique challenges for materials design.
To handle these larger ions, materials store sodium in several ways. The most common is intercalation, where ions slide between layers of a material, like cards in a deck.
Other mechanisms include alloying, where sodium forms a new compound with the anode material, and conversion reactions, which involve more complex chemical transformations.
Each of these storage methods affects the battery's performance, which we measure in a few key ways. The most famous is energy density, which tells you how much energy can be stored for a given weight.
For any battery to be practical, its performance must be stable over time. That's where cycle life comes in, which is the number of times a battery can be charged and discharged before it significantly loses capacity.
Let's talk about the components, starting with the cathode, which is a critical part that determines the battery's voltage and capacity. Layered transition metal oxides are a common type, similar to those used in lithium-ion batteries.
While they offer high capacity, these layered oxides can become unstable during cycling, leading to performance fade. Researchers are constantly working to improve their stability through techniques like elemental doping.
For better safety and a longer life, another class called polyanionic compounds is very promising. Materials like NVP, or sodium vanadium phosphate, have a robust 3D structure that prevents them from degrading quickly.
Then there are Prussian blue analogs, or PBAs, which are really exciting because they're made from low-cost, abundant materials like iron and have a very open framework. This structure allows sodium ions to move in and out very quickly, which is great for fast charging.
On the anode side, the material choice is just as crucial. You can't just use graphite, the standard anode in lithium-ion batteries, because the larger sodium ions don't fit well within its layers.
So, the go-to anode material for sodium-ion batteries is hard carbon. It has a more disordered structure, with various pockets and layers that can easily accommodate the sodium ions.
But what if we could get rid of the anode material altogether? This is the idea behind a transformative new design, the Anode-Free Sodium-Ion Battery, or AF-SiB.
In this design, there's no pre-installed anode. Instead, pure sodium metal is plated directly onto a current collector during the first charge. This approach simplifies manufacturing and can dramatically increase the energy density.
Plating sodium smoothly and repeatedly is a huge challenge. If it's not controlled, you get needle-like structures called dendrites, which can cause the battery to short-circuit and fail.
To prevent this, researchers are engineering the surface of the current collector. By applying special coatings or creating 3D structures, they can guide the sodium to deposit uniformly and safely.
The electrolyte, the liquid that transports the ions, also plays a pivotal role in anode-free designs. Special high-concentration or localized high-concentration electrolytes help form a stable protective layer on the sodium surface.
So where will we see these batteries? Because of their low cost and safety, the first major application for sodium-ion batteries is large-scale grid storage, helping to integrate renewable energy from wind and solar farms.
And while they're a bit less energy-dense than lithium-ion, they're already appearing in moderate-range electric vehicles, especially in markets that prioritize cost and sustainability. Ultimately, sodium-ion batteries represent a crucial step towards a more diverse and sustainable energy future.